Okay, welcome everyone. Today we're going to start a new chapter. We're going to talk about sequences and finally series. So our objective today is talking about the sequence. Well, what is a sequence? Definition of a sequence. A sequence is a function. A sequence is a function. It means that you have some input values and you have some output values. So here you have a machine. This is your function. The name of this function is sequence, and you have your, so here you have your function. Here you have some input values and some output values. Okay, input values, inputs. And then that function might or might not change those input values and give you some outputs. Okay, outputs. The thing is that when it comes to sequences, we restrict the input values. We usually take them from natural number set. So the input values are natural numbers. They belong to natural numbers. 1, 2, 3, 4, and so on. This symbol means belong to. So the input values are members of natural number set. Belongs to. So this function that we call a sequence takes natural numbers. Note that in some other books or in other examples, we might start from 0 as well. So we might take whole numbers as well. So this sequence, this function takes on natural numbers or whole numbers and give you some output values. So a sequence is a function A sub n, or denoted by f of n, with domain natural numbers, or again, sometimes we work with the whole numbers, with domain equals to n natural numbers, 1, 2, 3, 4, and so on, and sometimes whole numbers, and it gives you some output values with range. The output values is A sub 1, A sub 2, A sub 3, and so on. Again, you're dealing with a function. Why we're interested in sequences? Because eventually we can take the terms of a sequence, add them together, and define something new that we call series. But for now, let us focus on sequence and the properties of a sequence, and eventually finding the limit of the sequence. Let's go over some examples together. Example of sequence. So let us start by taking this sequence. A sub n or f of n is equal to n divided by n plus 1. Similarly, what you learned in elementary calculus was, okay, if I use x in terms of n, I can define this function. So if this is recall for you, that f of x was equal to x divided by x plus 1 in elementary calculus. When you're talking about sequences, you're dealing with n natural numbers. What's the meaning of that? It means that a sub 1 is equal to f of 1. By substitution, we get 1 divided by 2. A sub 2, or f of 2, is equal to 2 divided by 3. A sub 3 is f of 3, which is equal to 3 divided by 4, and the rest of the terms of the sequence. This is your first term. This is your second term. The third term, and we call this guy the general term of the sequence. So a sub n equals to f of n, which is n over n plus 1. This is the general term of your sequence. We can continue this. You can find the next term, which is a sub n plus 1, a sub n plus 2, and continue this process, finding the rest of the terms. Well, you should be asking why you're mentioning f of x equals to x over x plus 1. Well, when n approaches infinity, the behavior of your sequence is similar to the behavior of this function that you learned in elementary calculus. It means that when you're dealing with the limit of a sequence, you can just treat that the same as the limit of your function, the limit concept that you learned in elementary calculus. What do I mean by that? Well, suppose in this example, the question says, okay, you have a sequence. It's not very interesting. Find some characteristic values for this sequence. For example, what is the limit of this sequence as n approaches infinity? What is the limit of a sub n as n approaches infinity? Or what is the limit of this guy, n divided by n plus 1, as n approaches infinity? What is this limit? How do I find this limit? At infinity, the behavior of sequence and f of x are the same. So since at infinity, the behavior of f of n and f of x are the same, the limit of an at infinity is the same as the limit of f of x while x approaches infinity, which is the limit of x divided by x plus 1 while x approaches to infinity, which is equal to 1. So you say that, hey, at infinity, the end behavior of this sequence is the same as the end behavior of this function, and it is equal to 1. My y value approaches to 1. Y value approaches 1. What's the graph like? It's not that hard to visualize this. Let us take a look at the graph using Desmos. You have x divided by x plus 1. And since when it comes to a sequence, we are only working with positive numbers, natural numbers, we consider the right-hand side, and it's not going to be continuous. This is function f of x. For your sequence, you're going to have f of n. You're going to have some dots. When n is 1, an is a half. When n is 2, you have 2/3. When n is 3, you have 3/4, and so on. So let us get back to the board, see the difference between these two. So the graph of f of x and the graph of f of n, the difference between them. This is some part of your f of x. X divided by 1 plus x. This is what you learned in algebra, how to graph this. When it comes to sequence, you have some terms. You are not allowed to connect those dots together. Okay, so what should we do? A sub 1, it means that when n is 1, your very first y value is a half. So it is 1, it's going to be a half. This is a sub 1. When n is 2, you get 2/3. N is 2, you get 2/3, a little bit above this. N is 3, you get 3/4. 3, and just a little bit up here, a sub 2. And it continues. It continues as some dots. So the graph is discrete. It's not continuous like this. That's the difference between a sequence and a function. This is n over n plus 1, but this guy is x over x plus 1. But again, when your n approaches infinity, your x approaches infinity, the end behavior are going to be the same. That's why the limits are the same. Yeah, it shouldn't go down, it should go up and stop at 1. Just make sure everything is correlated here. Okay, perfect. Well, here we have the general term, we plug in some values, and then we write down some of the terms in the range for this function, and we use dots to visualize that in the plane. Now I expect you to ask, what if I have some terms? How do I write the general term of the sequence? Okay, let's go over one example together. So this example says, well, what do we have? We have this guy here. A sub n is equal to 3/5, comma, -4/25, comma, what else do we have? 5/125. The next term is -6/625, and so on. What is the general term for this sequence? Okay, general term for this sequence. On the denominator, it's not very hard to see that it is the exponents of 5. 5 to the first power, 5 to the second power, 5 to the third power, and so on. On my numerator, however, I see positive, negative terms. Positive, negative terms, 3, 4, 5, 6. So it means that there is a negative one raised to some exponents involved. So I have negative 1 raised to something, and then I have 3, 4, 5. So something is going on my numerator. On my denominator, however, I have 5 raised to power n. Okay. So when n is 1, this guy must be positive. So it must be n plus 1. If it was just n, I get negative 1 on my numerator, and this guy must be negative 3, not positive 3. So I figured out the exponent for my negative 1. What about 3? If n is equal to 1, I need to get 3. If n is 2, I need to get 4. It seems like that if you write it as n plus 2, it's a good choice. It's a good choice here. So let's double check this. If n is equal to 1, the very first element in the domain is 1. A sub 1 is negative 1 to the second power, 1 plus 2 divided by 5 to the first power, which is 3 over 5. I get my first term back. N is equal to 2. A sub 2 is negative 1 raised to the 3. And here I have 2 plus 2 divided by 5 squared, which is negative 4 over 24. So by checking these terms, you can see that the general term of the sequence generates each of these terms here. Now you should be asking, what is the limit of this sequence? What is the limit of a sub n as n goes to infinity? Remember that when it comes to sequences, you're interested in end behavior of the sequence. You're not really interested in the finite elements or terms of the sequence. You're interested in, okay, how does this sequence behave while n gets larger and larger, goes to infinity? What is this limit? It means that we need to remember what we learned in elementary calculus, review the limit techniques to be able to find the limit of this sequence. It's the same as limit of function f of x as x approaches infinity, which is the limit of negative 1 to x plus 1, x plus 2, divided by 5 to the x as x approaches infinity. Remember that what you learned before is that on the denominator, you have an exponential function. Exponential function goes to infinity much faster than linear function. And this is just negative 1 raised to some exponent. It is positive 1, negative 1, positive 1, negative 1. Here you have a number. Here you have a linear function. And down here you have exponential function. Exponential function goes to infinity much faster than your numerator. So you have some scalar divided by infinity. It is 0. Goes to infinity very fast. And here you have some scalar. So it's going to be 0. So the limit of this sequence while n goes to infinity is 0. Okay, let us go over some important definitions. So we're going to talk about a convergent and divergent sequence. definition of a limit for a sequence, limit L for sequence. So when the limit of your sequence as n approaches infinity is equal to a number like L, we say that L is the limit of your sequence. Then we say L is the limit of the sequence. In this case, we say that the sequence is convergent to L. We say that the sequence is convergent to L. Convergent to L. Okay. What if it doesn't have a limit? In that case, we say that the sequence is divergent. If not, we say that the sequence is divergent. So convergent sequence, divergent sequence, these are the terminologies that we use when you're dealing with sequences. Okay. Example. I'm going to give you these sequences, and then we're going to check to see which one of them is convergent, which one is divergent. The very first one is 1 over n, 2, 1 over n squared, 3, 1 over square root of n, 4, 1 over n to negative 1, 5, 1 over n to negative n. Just a bunch of sequences, and we're interested in to check to see which one is convergent, which one is divergent. 1 over n, the limit of 1 over n, while n approaches infinity, is 0. We all know that. The limit of 1 over n squared, while n approaches infinity, behaves the same as 1 over x squared. It is 0. So instead of keep writing x, I'm just going to refer back to n. But you know that when we are talking about the limit of 1 over n, we're actually taking the limit of 1 over x as x approaches infinity. The same as the function that we learned in elementary calculus. What about this? The limit of 1 over square root of n, while n approaches infinity, this is also 0. What about this guy? I have 1 divided by n raised to a negative exponent. If I rewrite this, I have n to the first power. The limit of n as n approaches infinity is infinity. Okay, it doesn't have a limit. Limit at infinity is equal to infinity. It's not a number. What about this guy? This is the limit of, this is equal to square root of n. Limit of square root of n while n approaches infinity is infinity. So here you have convergent sequence, convergent sequence, convergent sequence, divergent sequence, and divergent sequence. Is there any conclusion here? Yes, of course. The conclusion is, if you have 1 divided by n to power r, as long as r is positive, then you have a convergent sequence. So let's write this down here. Here's a note for you. The limit of 1 divided by n to power r, while r is positive and approaches infinity is equal to 0. So the sequence an, which is 1 over n to power r for positive r values, is convergent. Okay, some more definitions, then we're going to go over a lot of examples. Increasing, decreasing sequence, and a sequence that is bounded. Definition of increasing, decreasing sequence. So a sequence like an is called increasing if n is less than n plus 1, then we can conclude that a sub n is less than a sub n plus 1. And a sequence is called decreasing. So this is increasing sequence. A sequence like a sub n is called decreasing if n is less than n plus 1, then you conclude that an is larger than an plus 1. It means that the terms of the sequence are getting smaller and smaller. Increasing and decreasing. In general, if a sequence is increasing or decreasing, we call it a monotonic sequence. So if you see monotonic or monotone sequence, it means that it's referring to being increasing or decreasing.
Professor, I have a question.
There you go. So let us talk about bounded sequence. Guys, when we're talking about sequence, what is important for us is the y value. Okay, the output values. Input values, I mean, okay, input values, they're coming from natural numbers. Of course, they are following specific properties. Those are natural numbers, 1, then 2, then 3, then 4, then 5. For sequences, you're interested in output values, y values. So when we are saying that, hey, a sequence is bounded, it means that the y value is bounded. Definition. Of bounded sequence. So a sequence like an is called bounded above. Bounded above. It means that if we can find a fixed y value, a fixed number, output number, that your y values, your output values, they don't go further than constant. So if there is a y value, again, guys, I'm specifically telling you, this is a y value. If a y value like M exists such that AN is less than M, and it's over your domain, the domain that you have. So as you go along on the x-axis, your y values, they don't go further than M. Very well. Like what? Like n divided by n plus 1. Remember that the limit was 1. N divided by n plus 1 is a good example. It's bounded above by 1. And the sequence is called bounded below. So this is bounded above. If your y values in your sequence are less than a constant like m, that constant is y value, not x, not n. A sequence like an is called bounded below. If there is another y value, there is a y value like small m, such that a sub n is greater than or equal to that m on its domain. So bounded below. How do you visualize this? Well, the visualization is not that hard. Let's take a look at this together. Suppose you have your sequence. This is your sequence, some points. And this guy is your M in the same color. This is sequence M. And this is sequence N. It might be here, it might be up there, it doesn't matter. This is your M. This is your M, capital M and small m. And your sequence is like this. Starts from this point, this point. This is sequence A. So as you can see, for example, for this sequence, it's bounded above and it's bounded below. So AN, the y values, are bounded between M and M. This sequence is bounded above and bounded below, so it's just bounded. Since this sequence is bounded above and below, we call it a bounded sequence. It has upper bound and it has lower bound. So when you see a bounded sequence, it quickly reminds you of sandwich theorem. Sandwich theorem was the theorem that you learned in elementary calculus. It was saying that, hey, if you have a function like f that is bounded by two functions like g and h, and if the limit of those functions, g and h, those exist, and they are both equal to a fixed number like L, then the limit of the middle function must be equals to L. We have the exact same thing when it comes to sequences. So squeeze theorem. Let AN is bounded between BN and CN. You have three sequences. If the limit of BN is equal to limit of Cn while n approaches infinity, both of them are equal to 1 to L, not 1, then the limit of An while n approaches infinity is L as well. This is called squeeze or sandwich theorem. Okay, give us some examples. Okay. Let us write down some examples here. Talk about the limit of sequences, make it a little bit more interesting. Examples. The first one, what's the limit of ln of n divided by n while n approaches infinity? 2, what's the limit of -1 to power n divided by n while n approaches infinity? And let me write this right here. 3, what's the limit of -1 to the power n while n approaches infinity? 4, what's the limit of sine of pi over n while n approaches infinity? And one interesting one, what's the limit of n factorial divided by n to the n while n approaches infinity? Interesting sequences. Again, remember that when we are dealing with sequences and the limit of sequences, this is nothing but elementary calculus, the limit of function f of x. For the first one, this is the same as taking the limit of ln of x divided by x as x approaches infinity. You remember this, right? It was infinity over infinity. Then you can apply L'Hopital's rule. It was the derivative of ln. The derivative of ln of x divided by the derivative of x as x approaches infinity. The derivative of ln of x was 1 over x, and the derivative of x was just 1, and x approaches infinity. This is the limit of 1 over x as x approaches infinity, which is 0. So we have a convergent sequence. This time, of course, the same as elementary calculus, what we learned before, -1 to the power x divided by x, x approaches to infinity. Here you have a scalar, +1, -1, and divided by infinity. So scalar divided by infinity, which is 0. Convergence. What about this guy? -1 to the power n. If you simplify this, you get -1 for n to be odd, and +1 for n to be even. So it's oscillating between -1, +1. It means that it doesn't have a fixed limit, so it is divergent. It does not have a fixed limit, so it is divergent. Okay, limit of sine of pi over n, which is the same as the limit of sine of pi over x as x approaches infinity. Since sine is a continuous function, this is the same as finding the sine of limit of pi over x as x approaches infinity, or sine of 0, which is 0, so it is convergent. Okay, for this guy, which is n factorial divided by n to power n, I'm going to use squeeze theorem. We mentioned that theorem, so there is a use for that. What's the use? Take a look at this. N factorial, as you remember, is 1 times 2 times 3 times 4 times n. So this guy is 1 times 2 times 3 times n. And on the denominator, I have n times n times n, n times. So I have n times n times n times n times. All right? Yeah, of course. We can separate these as 1 over n times 2 over n times 3 over n dot 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 n over n. So this fraction is sandwiched between 0 and 1 over n. As n approaches infinity, the limit on the right is 0, the limit on the left is 0, so I claim that this limit is equal to 0. Okay, so now think about this sequence, R to the n. Sequence R to the n. R is a number. Okay, this sequence, if R is equal to 1, if your R is equal to 1, then it means that you have R 1 to power n, which is 1, so it's always convergent to 1. If R is less than 1, greater than -1, it means that if you have a half, a third, negative, a fifth, negative, a fourth, and so on, you get a fraction raised to infinity, and that fraction is sandwiched between -1 and 1. It means that it's a small fraction, so it's going to be the limit is going to be 0. And again, we have a convergent sequence. So when you have a sequence, a sub n equals to r to the n, this is the behavior that we expect from this sequence. If r is equal to 1, you say that, hey, this sequence is convergent to 1. If r is in between -1 and 1, 0, a half, a third, those fractions, then the limit also goes to 0 and it is convergent. So another example for you. This example says, well, show that this sequence a sub n, which is equal to 3 divided by n plus 5, is decreasing. We're going to have two approaches when we solve a problem about increasing, decreasing sequences. The very first approach is to use the definition. So first approach, use direct definition. What was the direct definition? It says, hey, if n is less than n plus 1, then you can conclude that an is larger than an plus 1. As we go along x-axis, increase on x-axis, our y values start decreasing. If you can show that a sub n is larger than a sub n plus 1, then you're done. Okay, so n is less than n plus 1. Our goal is to show that your y values, your terms, are getting smaller and smaller. N is less than n plus 1. Our goal is to construct this function. N is less than n plus 1. By adding 4 to both hand sides, we can just create what is missing there. Am I right? Oh, this is 5. By adding 5 to both hand sides, we can create that. So add 5 to both sides. So n plus 5 is less than n plus 6. Okay. N plus 5 is on the denominator. So I'm going to flip both sides. Add 5. Flip these terms. Okay, if I flip this, it's like, remember that if you have 2 less than 3, a third is less than a half. When you flip these, it means that the first one gets the denominator 3 and the second one gets the denominator 2. So it's going to be like 1 over n plus 6 less than 1 over n plus 5. What else is left? 3. It must have 3 on its numerator. So if I multiply all sides by 3, then I'm done. By 3. So 3 divided by n plus 6 is less than 3 divided by n plus 5. What is this guy? This is my an. What is this guy? This is an plus 1. So the conclusion is an is larger than an plus 1, and we're done. This is the very first approach that you can use the direct definition. Now, the second approach. Remember that I kept telling you, hey, guys, this is your actual function that you learned in elementary calculus. So Remember, in elementary calculus, they say that a function is decreasing if the derivative of the function is negative. Recall that a function is decreasing if its derivative is negative. Well, I'm going to take the derivative of this function and show that the derivative is negative on its domain. So f of x is equal to 3 divided by x plus 5. F prime of x, you can opt for quotient rule or just flip this guy. You get 0 times x plus 5 minus the derivative of this guy is 1 times 3 divided by x plus 5 squared. So the derivative of this function is equal to negative 3 divided by x plus 5 squared. The denominator is always positive. The numerator is negative. So this is always negative. Since the derivative is negative, so we have a decreasing sequence. Another smiley face for you. Both of them give you the exact same result using the direct definition, using the derivative, what we learned in elementary calculus.
Professor, I have a question.
Awesome. Two theorems. So the first theorem says, if the absolute value of, so when you're taking the absolute value of a sequence and then taking the limit of absolute value as n approaches infinity, this guy is equal to 0, then we can conclude that the limit of our series, our sequence is also 0. If the limit of absolute value of the sequence is 0, then the conclusion is that the limit of that sequence is also 0. For example, think about an to be negative 1 to the power n divided by n. What is the absolute value of an? The absolute value of an is the absolute value of negative 1 to any power is 1, and the absolute value of n is already a positive number, it's going to be n. So if I take the limit of absolute value of an while n approaches to infinity, I know this guy is the limit of 1 over n approaches to infinity is 0. Okay. This theorem says, since the limit of absolute value is 0, then I can quickly conclude that the limit of negative 1 to the power n divided by n is also 0. So when you're dealing with sequences that have negative 1 to some exponents, first find the limit of their absolute values. If the limit of absolute value is 0, then you can quickly conclude that the limit of your sequence is also 0. And finally, every bounded monotonic sequence has a limit, it means that it is convergent. So theorem, every bounded monotonic sequence is convergent. So if it's not convergent, if it's divergent, it means that it's either not bounded or it's not increasing or decreasing.